So now that we've talked about the simulation of visualizing these standing waves, let's do the mathematics of them. So basically, a standing wave is when you have two traveling waves of the same wavelength coming towards one another, right? They're coming in towards one another, then eventually you're going to see this pattern where every point, adds up together with every other point. And so you see this one wobbling up, this one wobbling down, this one wobbling up, this one wobbling down, this one wobbling up. And that's technically everywhere on the x-axis. If you have two waves of the same wavelength traveling in opposite directions, that's the shape that you will graph. You'll graph just a two sine wave oscillating up and down everywhere. And so we can certainly restrict our attention to a special length. And so let me talk about the math of it. Let's look at this wave on a string. So let's just do the node and let's just do the node pair. Okay. So how do I create this first pattern? String has a length of L. So how do I produce this pattern? I have to send in a wave. If you notice that very first pattern that we formed kind of looks like this. And this is the picture that's often drawn for standing waves. Sometimes it's hard to understand, right? This is the picture that we draw to represent the standing wave up and down. This is like the wave at sequential intervals in time. This one little sine bump is only half the wavelength. And so in order to produce a standing wave of that first fundamental, you actually have to send in, and I'm actually going to draw the string a little bit further. Oops, went too far. You actually have to send a wave of twice the wavelength into the string. So this lambda is 2L. So what'll happen is, besides the first initial part where the fixed end will send, you'll send in this wave, right? And when you send in this wave, then you've got the reflected one coming back on it. So you have two waves of wavelength 2L interacting. Now we know that the speed of a wave is equal to the wavelength times the frequency. So the fundamental frequency, I'm going to call it F harmonic, HAR for harmonic, is shown to be the speed of the wave divided by the wavelength, which is 2L. So this is the starting point for all of the other patterns. And of course, for our simulation, if you remember, we had a frequency of 0.4 hertz. I remember the speed of the wave was like, I think it was 6 centimeters per second in the simulation. And so evidently we must have had a length of the string equal to 12 centimeters. Right? No, it's not. To make it 0.4, my brain's not working well. So 6 divided by 0.4 is 15, actually. So it's 7.5. Yeah, 7 point. So evidently the length of our demo string is 7.5 centimeters, for what that's worth. But this is the 0.4 hertz. This is the 0.4 hertz for our picture. Period of 1 over 0.4 hertz, which is 2.5 seconds, right? Okay, so that's the fundamental harmonic. And what about the next one, right? To create the next pattern, you had to send in, now you send in a wave of equal to the wavelength, where the wave whose wavelength is equal to the length of the string. So it's double the wavelength, or half the wavelength, double the frequency. So this is lambda equals 2L. And although I don't see it on the picture, I can't stress it enough that when the thing hits the boundary, it reflects. And so there's like a second wave. There's like a second wave coming in from the other side that's also lambda equals L. right? And so when they add together, that's when you get this second pattern. So the wavelength is reduced by a half. That's the pattern. The book has the pictures that are a lot nicer than this. But so the wavelength is halved, which means at constant speed, the frequency is doubled. And so here you get that the frequency of what we call the second harmonic is doubled. And as a brief aside, this is something that happens more often than you think. Okay, when you hit a guitar string, sometimes that A string, that's 440 hertz, when you pluck that string, technically you hear the 440 hertz, but sometimes you also hear the tiny part of the 880 hertz as well. We have a physics of sound lab where they really explore some of these things. We got some really neat tuning forks in the demo room for what that's worth. When you hit those things, you hear the first frequency, but you also hear the second frequency. So this is F, the second harmonic, and that's 2FHAR, the fundamental harmonic. And so the pattern, hopefully you can see the pattern, is that for the third mode, where there's 3 of these full bumps, then F3 is equal to 3 times the fundamental harmonic. So what's the wavelength then? The wavelength has to be 2/3 times, the wavelength has to be 2/3 because you have the pattern, the symmetric pattern like that. Right? And so the wavelength that you send in has to be lambda equals 2/3 in order to make the frequency triple. And then so the pattern that forms, you know, in calculus 2, you talk a lot about sequences and series. The sequence that forms for the wavelengths, well, the sequence for the frequencies is easy, right? The frequencies just, you know, increase by a multiple of F harmonic. But the wavelengths, they decrease. They decrease proportionally. They go from 2L to L to 2/3 L to 3/4 L, and not 3/4 L, but 2/4 L. So it'd be L, and then so 2L, and then L, and then 2/3 L, and then the next one would be 2/4 L, and then it's actually 2/5 L, and then 2/6 L, and that's how those frequencies, that's how the wavelengths increase. So the wavelengths are a decreasing, they're a decreasing sequence that goes like 1 over the length, or 1 over n, basically. So the fundamental frequency, so in general then, and this will be helpful kind of to make as a little study guide. So for a node-node pair, okay, so the fundamental harmonic is the speed over 2L, right? And then every subsequent harmonic for n greater than 1 is just equal to n times the fundamental. That's for the frequency. But what about the wavelength? Well, the wavelength of that first harmonic is 2 over L, and then of course that means going to make the wavelength for any successive harmonic just 2L over n. So this is the one that's easiest to understand. Like for n equals, well, I mean, this is like n equals 1. That's like the n equals 1 fundamental harmonic. Sometimes it's called the first harmonic, or the fundamental harmonic. And so that one's pretty clear. What about for the node-antinode pair? The one where there's a loose end. What's different here? Well, I'll just do slash actually. Node, antinode. Now the fundamental harmonic is half of this, right? Because it went from 0.4 to 0.2 hertz, and so it's V over 4L. So how do we figure out the pattern here? it's V over 4L, but you don't keep adding V over 4L because you would get to these ones which are inaccessible to the node antinode combination. So what is the pattern? Well, you can work it out with scratch paper. It's like the first one would be V over 4. Oops. The second harmonic, F2, would be V over 4L plus V over 2L. Right? So F3, what would be the third one? We're adding 2 copies of these. So that's not double the frequency, but it is, so if you go, that's 0.6. So if you start at a 0.2 and go to 0.6 and then go to 1, what's that sequence then? Well, it's 0.4 times V over 2L, but with this extra factor. So you sometimes include a minus sign in it to show that it is V over 2L V over 2L. Oh yeah, okay. So it would be N. So it would be, that'd be N times V over 2L minus that consistent V over 4L. So F sub, oh, sorry, that'd be F sub N, excuse me. So you'd have F sub N equals what? If you factor out the L's and the V's and the 2's, you get V over 2L N minus a half. And that is the fundamental that is all the frequencies that are accessible to the node antinode pair. Does that work? Yeah, you're always adding a half. Yeah, or you're always subtracting the half. And this even works for N starting at 1. Yeah, because when you start at 1, it's exactly, when you start at 1, it's exactly half of that V over 2L, which was for us was 0.4. So the wavelength then, the wavelength is starting to get even more confusing for the fundamental wavelength. The fundamental wavelength has to be 4L. And then because when you looked at that pattern on that string, right, you only saw the first quarter bump, right? But that kind of back projects to an entire wavelength. So you have a wavelength of 4L, but you only see the first quarter of that wavelength. So the wavelength is 4L, and then sure enough, you can do some algebra to show that this obviously, so this equals V over the fundamental frequency, and so you can solve for V1 as well. So that's the node combination here, and that's the antinode combination over here. This is really interesting results. Oh, by the way, the antinode pair actually comes back to this pattern as long as you're aware that the 2 ends are always antinodes. So the antinode shares this node-node combination, okay? Because again, any other frequency and you don't see a nice pattern, you see jumbled mess, okay? So going back, now what are some other examples of standing waves? Well, you'd be surprised to know that they show up in light as well. An example that is on a common YouTube video is where, I think the guy is Dustin from the channel Smarter Every Day, not paid for any of these channels, but for advertising, they're just good. So what he does is he puts a square piece of cheese that is the entire base length width of the microwave. And what he finds is that when you microwave it, there's areas that are burned and there's areas that are not burned. And so when he took that cheese and put it in the microwave, he found that there are these Yeah, these layers of burning, depending on, and you can use this to actually measure the wavelength of the microwaves that are in the actual microwave. Okay, a laser is another example of a standing wave pattern, and so this would be like evidently the microwave. In this case, it's a node pair, so it's a node at the end, so the wave is 0 on the both ends. So if there's 4 antinodes in the middle, then this is the 1, 2, 3, 4, fourth harmonic. This would be the fourth harmonic. Lasers, are a small cavity where light of a very high frequency, very tiny wavelength is traveling. So even a laser that's a couple centimeters long, whose cavity is a couple centimeters long, has a harmonic that's in the millions, the millionth harmonic or so of the light that's formed, because lasers more or less just a mirror, a couple mirrors that the light bounces off, and you have to tune it correctly. And there's a tiny little bit of gas in here, that in the laser, that when you push on the button, that activates a little circuit that puts a little field in there, electric field, which causes the gas molecules in the gas, the outer electrons, to jump up and then spontaneously emit light as they're going down. That's the phenomenon of lasing. It's the light amplification of the stimulated emission or spontaneous emission of radiation. Well, it's technically stimulated because you put a field in it, but then spontaneously emitted itself. Oh, other examples, sound, musical instruments, right? There's a nice section in here about flutes and brass instruments, of how they're able to create change the shape of the cavity to change the sound. Trumpets, clarinets, it's woodwind and brass instruments takes advantage of standing waves inside the sound inside the cavities of the materials, and so they're everywhere, and all of the mathematics translates perfectly well into those settings.